Hi everybody, we're back for the second part of the first lecture. The reason we had to cut it in pieces is because it doesn't, any of the videos over an hour seem to not lend them so well to putting on YouTube. Probably working on that issue to see how far we get. So part two of the first lecture is this continuation of some of the parameters around a sine wave. We looked at peak voltage, peak to peak voltage, instantaneous voltage at a particular angle, and period and frequency. And now we have two more values that we have to cover that are important, and that's average value and effective value. And two very commonly used transformations of the values of peak that we use quite often in electronics or electrical work. So let's get started on that. That's fairly quick. So the average value, let's talk about averages first in general. And here's an example of an average of a pile of sand. Okay, and it has an odd shape, and it kind of looks like a pulsed side of one half of a sine wave, a little distorted. And what is the average height of that pile of sand? We have a distance, or like say there's a bucket or something that we're putting it in, and it has a certain width. And we squish this sand down, and eventually it takes a nice level height across the bucket. All right, that becomes the average. That's the average height of that pile over a certain distance. So that's a form of doing an example of an average. Pushing the dirt down, the odd shaped pile of dirt down flat, so it's regular across this width, and that becomes the average. So we know that average changes with the width of the bucket. Obviously, if the bucket's narrow, it's going to be higher. If the bucket is wider, it's going to be lower. So here's a case where we have the pile of sand, and we pushed it down into a bin or a bucket that's much wider than the last one. So you can see that this height is much less than the previous example. All right, so that's important to look at. The analogy here is the distance could be the time that it takes for one complete cycle. All right, we'll talk about that. But imagine this being a half a cycle of a sine wave, all right, and this not being distance but time. All right. So in the second example, we have a little bit of we have a pile of sand, and then we have a reduction of sand over a cycle, and you have to find the depression. You have to find the algebraic difference of what's up here and what's down here, and that gives you a different average as well. So if you don't have a complete sine wave going across, you only have a partial. These are considerations to how this depth is, okay, related to the sand, is really the amplitude of the sine wave, or half a sine wave in this example. Averages, these are just basic averages. If you have a pile that's 5 feet high and a pile that's 5 feet down, your average is obviously 0, right? Because you have a +5 and -5, and you wind up with 0. The other time we can use an average example, very, very common, is you're on a trip and you want to find out how long it took to get someplace and what was your average speed. So we use our navigation programs and various things on our phones, Google Map, and we put in how long does it take to get to Pittsburgh, and it comes up with 6 hours and 41 minutes. And it takes us, in reality, 10 hours, because Google didn't calculate us stopping to look at the beautiful scenery, going to the bathroom, or stopping for lunch. So if the reality of this average time is not what you'd read on your phone. So here's an example of an automobile traveling for it looks like 2 hours at 60 miles an hour, and then they took like a lunch break, and then went back and, you know, the travel conditions changed, and now it's, what does it look like now? 50 miles an hour? 50 miles an hour for another 1, 2, 3 hours over here. So your whole time you drove, or the whole time you were out on your excursion was 5 hours, but you weren't driving the same speed or driving at all for part of that. So what you have to do is come up with the total time it took and the total distance, and you work out what your total speed is. So in this case, the average turned out to be somewhere right in there. That was your average speed, which looks like around 45 miles an hour. So another case of an average. We use averages all the time. I will use an average to do your grades. I'll add them up and divide by 14, whatever it is, and come up with an average. So again, here's finding the average value of 1/2 of a positive pulse. We call 1/2 of a sine wave a positive pulse. All right, it's really half of the sine wave, as opposed to here's a full sine wave over one cycle. This is half a cycle. So this is how we find the average for this. All right, so let's look at this example for a minute. All right, we have that, which is positive, right? And let's just say it's climbing from 0 to some number, 10, and back to 0 again. And over here we have 0 minus 10 and back to 0 again. What do you think the average would be for that? One full cycle, it goes positive and then switches over to negative. Since I can't hear you right now, I will answer. The average would be 0. Okay, the top would the first half of the cycle cancels out the second half of the cycle, and if we were to take this and measure it with a DC meter, right, or take our multimeter and put it in DC, would come up with 0. If you take your DC multimeter and plug it into the wall receptacle in your home or at school, it's going to read 0. That's the average voltage of what's coming out of that receptacle. So when we're talking about a half a cycle, or the pulse of a sinusoidal wave, just the 1/2, there is a value associated with that. All right, just the one piece over 1/2 a cycle. Let's call this a full cycle, and let's call this half a cycle. So over the half a cycle, the average is the peak value. All right, in this case they call it amplitude maximum. Right, you'll see variations in the book all the time of how they denote values of voltage and peak voltage. They'll change letters around, call it amplitude, so it's always a little confusing. So in this case, the peak amplitude, the peak value of this sine wave, the peak there, times 0.637 will give you what the DC equivalent is, what the DC voltage is. So if I was to take a DC meter and I have this signal coming out, and somehow I can measure it, it would read 0.637 times peak. So if I had 10 volts peak, it would read 6.37 volts. This is very important. We'll do some examples in a minute. This is very important when designing power supplies, trying to select the transformer to give you what you're going to need for output of the power supply. Right, so that's the average over that time. So this average is 0.637 times the peak. 63.7% of the peak is the average over 1/2 a cycle. So let's talk about this a little bit, about what's happening here. So we have, if you look at this example, what this is, something we're not going to be responsible for, but you'll certainly see it again down the road. This is converts AC to DC, and this device is called a bridge rectifier. Kind of hard to see in the picture here. But what a bridge rectifier does, rectifiers first of all are check valves for electricity. They allow the current to flow in the direction of the arrow and never back the other way. So interesting example, we have ventilators made in Germany. The translation in the manual was a little messed up. It said that one of the things we were talking about with check valves, and we knew there was no water or pneumatics involved in this, so we realized that they had never converted the check valve to rectifier or to diode. So for a positive, for a full wave rectifier, what it does, it takes the positive half of the cycle, and let's imagine that it's going up like this, right? During that cycle, this is positive. There's the direction of the arrow. It guides it over here, and that becomes positive. All right? And then it comes back this way, and comes back and completes the circuit that way. And that gives you this. It allows the positive part of the half of the sine wave to pass through. What's clever about the bridge rectifier is that on the negative half of the cycle, when this is going down now like this, right, it steers this, right, against the arrow. So let's look at this for a minute. So this would be the negative sign, so it's negative, and well, it's a little easy to probably see. Well, you can see it this way. You have the negative side, it routes it through, back over here, and that's negative. That comes back and follows negative that way, up into the other side of the source. So what it does, it takes that negative going half of the sine wave in that cycle and flips it so that it's up on top. So what this gives you is these pulses that are always positive, these pulse sinusoidal waveforms that are always positive. So this is positive, that's positive, the next one will be positive. You never have the bottom half. It's a steering circuit that steers the current so that you always have the positive piece. So what this becomes over time is the equivalent of 0.637 times the peak of the sine wave, and that becomes what the DC equivalent is. So in this case, if we had 10 volts, it would be, this output of that would be 6.37. A little more complicated than shown. We do add things like capacitors that charge up, that never let this to happen. They charge, and then they discharge a little bit, and we make it as flat as we can so that we get the ripple, what they call ripple, out of the power supply. All right. So that's with a full wave rectifier. So if you look at what happens with a half wave rectifier, the first part of the cycle, the current flows through. We have positive and negative, and you get this. The negative half of the cycle, it doesn't let the current pass. That's negative, and it doesn't let it pass, and you wind up with this dead space in here. So half the cycle is nothing, and the part of the cycle, the first part of the cycle, is your pulse coming through. So for this, you wind up with the average being 0.318 times whatever the peak voltage is. So if you choose to make a power supply using a half wave rectifier to go from AC to DC, you have a great loss there. In order to get the voltage you need out, you have to start off with a higher voltage in the transformer. You have to start off with something higher because you're only getting 31.8% out of this rectifier. All right, so whatever this is has to be much higher if you're trying to get a higher voltage out from it. So for half a cycle, the pulse average is 0.637, and if you run it over the equivalent of a full cycle, and the reason I show this example with the diodes is that this is an application for that. This would repeat. You'd only have a pulse, a space, a pulse, a space, a pulse, a space, and you only wind up with 31.8% of the output voltage. So that would be the two things you need to, the takeaway for this would be that the average voltage is the equivalent DC voltage. Not to be confused with what we're going to cover next, but if you took a meter and put it on that circuit, you'd measure, if you start off with 10, you'd measure, on DC, you'd measure 3.18 volts. Right? So when you're designing power supplies, doing anything with power, you know that the AC coming in, the average of the AC is the DC level, or the most DC that you can get out of the circuit. All right. And here's an example again where it shows the half a cycle. the half a cycle, and then dead space. So now we're talking about the average over this instead of the average over that. Right? So since the average is over a full cycle, it's only 31.8% or 0.318 the peak. Right? Two things to remember. What it is for a half a cycle over a half a cycle, this pulse only, and what it is over that. And the reason you're remembering that is because if you're building power supplies or anything and you want to have the most out of it, you have to capture that negative half and flip it upside down. Right? It's a steering circuit, the bridge rectifier. It steers the current. Years ago, if you had battery-operated devices and you put the battery in backwards, it would usually blow out some circuitry. So then somebody was brilliant enough to use a full-wave rectifier on the input, so you could take the battery and flip it any way you want, and the current would always steer in the direction of how the diodes were set up. Kind of a clever way to do that. All right, that's average value. And here's something kind of important. Estimating values. So it's very important to have accuracy in a lot of things. You want to be able to calculate things accurately, especially if you're more in the engineering field. In a practical sense, if you're a technologist of some kind, you probably want to be able to learn how to average, to take estimates on things, how to look at things and estimate what they should be. So here's a case of a waveform that might be on your oscilloscope, and your boss or somebody says, what do you think, give me a ballpark figure what this estimated value is. All right, and you'd kind of just like in your head kind of do some averaging. Well, this is, that's low, that's high. Come up with some kind of number there, and then you have this over a period of time and come up with something like that being the average. All right, it's a guesstimate. But guesstimates are very important and time savers when you're trying to do things. All right, once you have a guesstimate that this is what it is, then you can drill down and get the actual results of whatever you need. But guesstimation, as we put it, is very important. All right, in troubleshooting particularly. The DC value, DC level or average value of any waveform can be found using a digital multimeter or an oscilloscope. All right. If you take your digital multimeter and set it to DC, not AC, and measure it, you'll get the DC equivalent of whatever AC voltage you're measuring. And that's why if you put DC across the outlet, you have a positive half of the cycle, a negative half. They cancel out, you get 0. If you were to rectify that so you have all positives, you'd wind up with the peak value of whatever that is times 63.7%, 0.637, and that would be your equivalent DC voltage. That's what the meter would actually read. Right? So here's a case where we're talking about the sine wave, but let me skip ahead here a little bit. We're going to talk about effective value. All right? I think that slides out of order. Effective value is a little different. Effective value is where an AC voltage will produce the same amount of heat or work as a DC voltage. Right? Not to be confused with the DC voltage being the average. This is where you're looking for the AC equivalent of a DC voltage. You have a DC voltage heating up a pan of water. What voltage in AC does it take to do the same thing? So they came up with this little example, this little test, where they take a resistor, put it in a pan of water with a thermometer, and they close the first switch, which is a DC supply here, which applies, this one's the AC supply, it stays open, and this applies current to the resistor, and as we know, the power is I squared R. So as the current is flowing through that resistor, it starts to heat up, and that's the power dissipated, and it heats the water up, and eventually the temperature of the water is going to rise to a certain point. So the way they do that, and they come up, they'll do that, and they'll take that number, whatever that is, and correlate it to a rise of 5 degrees or something like that. All right. Once they have that, they bring the pan back to where it was, back to neutral, whatever the temperature was. Right. Obviously open up the switch so there's no DC current flowing. And then they close the other switch and vary the AC voltage until they can create the same heat in the resistor and raise the temperature of the water to the same point. Right? Once they do that, they have a voltage that they record as DC, and they have a recorded voltage that's AC. And there's some correlation between those two. But there is an equivalent voltage of AC that equals the work, the power that was generated by the DC voltage. Right? That's the effective value. That's how we describe the effective value. It's the voltage, AC voltage, that produces the same amount of heat in the resistor, in this case, or work, some kind of work, as the DC voltage. So the relationship is basically a function of the square root of 2. All right, so in this class, I have classes where everything that they just got out of high school and everything had to be kept in radical form to keep things very accurate. That's fine, except we have no instrumentation that reads out in radical form. All right, so in here, square root of 2 is equal to 1.414, and that's good enough. All right, we don't have to take it out to more digits than that. The reciprocal is also good to know. The reciprocal of 1.414 is 0.707. Those two numbers are something you'll be using back and forth and back and forth. So the relationship of the AC to the DC is, in this case, and it's talking about current in this case because we're talking about the power. The AC current is, if you take the maximum current divided by the square root of 2, that's equal to the DC current, right? Likewise, if you're finding the peak current down here, the peak current is equal to the square root of 2 times the DC current. See, we have this in voltage here somewhere. Well, here's the current again on the top. So the effective current is the peak current divided by square root of 2, right? Or the 0.707 times the peak current times 0.707 of the peak. All right, this likewise here. Voltage, the same deal. When we're going from effective voltage, we take the peak voltage and divide it by the square root of 2. And if we're looking for the peak voltage, we multiply it by the square root of 2. So another way of saying divide by the square root of 2 is just multiplying it by 0.707. So when we're trying to find the effective voltage, we take the peak voltage, multiply it by 0.707, and when we're trying to find the peak voltage, we multiply it by 1.414. We'll do some examples in a minute. But that's the relationship here to that. That correlation to the AC equivalent of the DC voltage needed to heat the pan of water, that's what it comes out to be. You'll notice in this class we don't do a lot of drilling down into the mathematics of things, which is probably a good thing. Engineering programs that would cover the same thing would spend a lot of time in trying to analyze where we came up with these numbers. But for the purpose of a class, more of a technology class, we accept the givens for a lot of the formulas that we do. So the equivalent DC value of a sinusoidal current or voltage is 0.707 of its peak value. So if you take the peak value of approximately 170 volts, all right, and multiply that by 0.707, I believe that's what I'm looking for here. Let me just throw that in my calculator. It always helps use a calculator. Let's see. 170 times 0.707. Yep. So 170 volts peak times 0.707 is 120 volts. And the reason 120 volts effective, or RMS. The reason I'm picking this number is the electrical voltage in your house, most of the time it's either 120 or 240. Right? That's the effective value. When you take your meter, your digital multimeter, and put it in AC, it's reading effective value. It's not reading peak. All right? So if you took your meter and put it in the wall and measure 120 volts, effective value, right? Now you look at that same output from the wall receptacle, whatever, on your oscilloscope, you're going to see a peak value of 170 volts. The peak of that sine wave is going to be 170. So there's the correlation that goes back and forth. You're going to be doing a lot of that in the lab. You'll be working with RMS, with your meter, and then they want you to look at it on the oscilloscope or convert it over or convert back from one to the other. And all you have to remember is the relationship of 1.414 and 0.707. All right, to convert the peak value, remember 170 volts for the wall voltage, 170 volts peak, times 0.707 is 120. All right, if you were trying to figure out what the peak was, you take your 120 and multiply it by 1.414, and that'll give you 170. So that's the relationship back and forth between effective. Right. Interesting, there's effective power ratings, other effective ratings like this, for current and voltage and power. And if you're buying a stereo system, some kind of a sound system for your home, the ratings for the audio output on it can be written either as peak values or RMS values. So if you sell it with peak values, it sounds like a lot more output than the RMS value. But you have to understand the relationship between those two. So somebody, let's use that 170 number. Say you buy a sound system, it says 170 watts per channel peak, and it's really only putting out 120 watts RMS. But you're comparing it against something else that you're buying where it says 140 watts, and you say, well, it's less than the 170, but no, 140 was RMS. You have to keep that in mind. You have to keep what voltage you're using, if it's RMS voltage or a peak voltage or peak to peak. Somebody might even make this system even sound greater by taking the 170 and selling the system and saying, oh, it puts out 340 watts peak to peak. I mean, you can play games with the numbers, but in the lab, you're going to do a lot of conversions back and forth. So get used to converting back and forth between those values. Effective value of a square wave. We don't do much with square waves, but what's interesting is the effective value of a square wave is the same as the peak value of the square wave. All right? We really don't need to know that because we don't use it very often. It's just good to know in the back of your head that you do not use the relationship of 0.707 or 1.414 with a square wave. Right? And it has to do with the fact, the function of it being a function of sine. Measurement. Most AC meters measure effective value, which they do. I can't think of any that they have with peak value. And it's of a sine wave, and not the peak or peak to peak values. The other interesting thing is that it'll be distorted if it's not a sine wave. Your values will be wrong. I might have mentioned this, I think I did in the first part of the lecture. Your function generators or signal generators always default to triangle. You have to remember always to press the sine button, the little symbol for the sine, to make it work in sine. All right. Especially if you're not using an oscilloscope and you actually don't see the waveform, and you're measuring with a meter, then you could have some pretty tragic results because the meter doesn't like triangle waves very much. It likes to see a sine wave. Designed for that. So the top meter is an analog meter. Uses a little scale with a needle on it, and the bottom one's a digital AC meter. Both AC meters, they both have the ones in the lab you'll be using are digital. So here's the problem we have. People have false assumptions that a digital meter is more accurate than an analog meter, and not necessarily the case. It's the circuitry that generates the digital display that is where the accuracy is. That doesn't have to be accurate. That doesn't have to be more accurate than that analog display. What it does do is take away interpretation. So looking at a needle against a scale, right, it's halfway between here and there, and something called parallax, that if you look at a meter this way, it has a different reading than if you look at it this way. All right, keep that in mind on analog meters. Something called parallax, supposed to look pretty much dead on to the needle and where it sits, but it doesn't necessarily mean it's less accurate than the digital meter. The analog meter also can see trends that a digital meter cannot see. All right, if you have a digital meter and it samples every so often, there's some kind of a sampling rate that's determined how often these get updated. Has to be, that's the way a digital meter works. Whereas this is instantaneous. So we use it for, in our medical equipment, we use it for output of stimulators, electrical stimulators that people use for physical therapy. If you connect you'll read the output the same down here, but if you were to move the amplitude adjustment up and down, and there's something wrong with it, say there's a dead spot or a spike, you'll never see that, but you'll see it here. You'll see a very quick jump that way or down, and that's why we look at our stimulators with both meters, but we look at them particularly with an analog meter when we're adjusting control. We don't want to have those spikes. That's something that's connected to someone's muscle generally, and the last thing they want is a pulse that's much higher than what they expect. All right, cause damage to your muscle, and it's not good. So we look at it so we can see the trends. We see the trend of it moving up nice and smooth and back again. Can't see that very well on a digital meter. The meter movement, I'm just going to go briefly over this. Sort of like the generator. We have poles of a magnet, right? And we have these are basically electromagnets. That's why we see the wire wrapped around them. And the center magnet that's connected to the meter, the sweep, is also an electromagnet. And what that does is when it gets energized, the opposite poles attract and the like poles repel and cause the meter to turn. Cause this to turn. Very clever setup. If you think about this, it looks very simple, but this has to be able to pivot, and you see these wires connected. So there's something called a Darcival meter, and it's amazing. I mean, years ago, you paid a lot of money for these because they used actually diamonds to pivot on. You did not want friction. Friction was your enemy. If you had friction, you couldn't get an accurate number. So that and these coils, these little springs that also acted as a feed for the voltage into the magnet. Not a very good representation. I think I might have one somewhere else of showing how this works, but very, very, very precision, very accurate device. Very temperamental. If you bumped it, it was done. So there's an advantage of digital over the analog. You could not drop those meters. You could not bump them. The whole movement would fall apart. So the Darcival movement was very, very clever design. Goes back quite a ways. Okay, so that's the end of the slides. Now I'm going to do some problems and review a little bit about the first part of the lecture as well. Okay, I have a problem on the board, and I gave you the peak voltage. I'll stand out of the way so we can see this. So given a sine wave with a peak voltage of 25 volts and a period of 1 microsecond, and that's 1 times 10 to the minus 6. Please get used to using the scientific notation for these. We're going to find peak-to-peak voltage, instantaneous voltage, average voltage, RMS voltage, and the frequency of the sine wave. So the best thing to do when you're working on a problem like this is actually draw the sine wave, and this way you get some feel for the visual of the wave itself. So first thing we're going to do is we're going to draw a sine wave down here on a plot. All right, keep in mind this is the 0 line, all right, in terms of amplitude. And this is the 0 line in terms of where things start in terms of time. All right, so if I know that, if I want to label this, first thing I can do is label the peak voltage on it. Gave you the peak voltage of 25 volts. This is the peak right there. All right, kind of speaks for itself. And that's 25 volts right there. All right, what else can we label? We can label I gave you the period. The time it takes for one complete cycle. All right, so we can run the line down here, and this is the period denoted by the letter T. All right, and we know that's 1 microsecond. 1 microsecond. All right, I'll also put on here that's 1 times 10 to the minus 6th. So that's the first thing I would do. I would label my problem, make a sine wave and label it so that you can work with that. Okay, so we have a few things to find here. So first of all, peak to peak, if this is symmetrical, which it is unless I say it's not, right? You have 25 up, you have 25 down over here for the other side. So this is minus 25, right? The difference between these two, if you have 25 positive and 25 negative, the total is 50. So your peak to peak is 50 volts, peak to peak. Right? I don't have to confuse it by putting that sign on there. It's 25 up, 25 down. You add the two together. All right, so peak to peak is simply twice the peak. Do not get confused by this. I mean, it seems like it's obvious, but when you're working with peak to peak, make sure you convert back to peak, because everything else you have to calculate is relying on peak value. Okay, because sometimes you'll get a lab where it'll give you the peak to peak value. Start with that. Okay, we need the instantaneous voltage at 60 degrees. All right, so remember this is one full cycle that runs from 0 degrees up here to 360 degrees. That's one full cycle. We know that at 180, 0, 180, and 360, the amplitude is 0 at those three places. We know that the peak voltage is, if this is 180 here, half that is 90. All right, so we know this is 90 over here. We know this is 180 plus 90 is 270 over there. So we know the two places where the signal is peak is 90 and 270. All right, so if we're calculating this based on the function of sine, we're looking for a place where it's 1 times the peak value. All right, so that turns out to be 90 degrees and 270. If you take the sine of 90 and the sine of 270, it'll be 1. Everywhere else, it's somewhere else. If you also take it at 0, 180, and 360, it's going to be 0. So here we're looking for 60, which is probably 45. I'm going to guess like right around here someplace. Let's say that's 60 degrees. All right, so that's 60 degrees. We find that by taking the sine of the angle times the peak voltage, V peak. All right. So in this case, it's the sine of 60 degrees times 25 volts. All right. So I want you to take your calculator and find the sine of 60 degrees. Make sure your calculator is not in radians. I will tell you this a million times during the course of the semester. It's a way to mess up an entire exam. I have to tell you also that I don't want you to use radians by accident even, but if you somehow have a really bad day and your calculator is in radians, I check over all the exams more than just the bottom line. This is why you have to always show all your work on an exam. I don't accept just the answer. If you show all your work, it works to your benefit. If you make a mistake and your calculator is in radians and I figure this out, you don't get a Zippo for the whole test. You lose some points, but not as much as you would if you just give me an answer and I have no idea how you got it. Very important to complete all your work. Very important to keep your calculator out of radians too. All right, so I'm as you should be, 60 degrees times the sine. I'm coming up with 0.866. All right, 0.866. So this would be 0.866 times 25. All right, which should equal, I don't know, we'll figure it out, times 25 is 21.65. 21.65 volts. That's what this is from here to here. This in here right there is 25.65 volts. Right? That's the instantaneous volts of this sine wave at 60 degrees. It's also going to occur over here on the other side of 90, right, where you take 180 minus 60 and have 120. So it's going to occur in 4 of the places on the sine wave where you have that. All right, so it's 21.65. The average voltage of this sine wave, of the complete sine wave as given here, all right, we have this and we have that. This is the positive half, that's the negative half. The average voltage of the sine wave is equal to also the DC voltage of the sine wave. And in this case, a total sine wave, the first half of the cycle cancels out the second half. We wind up with 0 volts. All right. If we were looking at strictly that piece right there, right, it would be 25 times 0.637. That's what we'd wind up with for that. But in this case, it's 0 volts. How about RMS? We want to convert from peak to RMS. Right? To do that, we take the V peak, all right, times 0.707 volts. 0.707, sorry. Right? So that would be 25 times 0.707. $17.68 approximately. 17.68 volts, right? Is that what I got? Make sure that's right. Approximately. Okay. That's the RMS value, right? So it takes if I had some work being done to heat a pan up or something, or let's say the brightness of a light, okay, 17.68 volts DC, it would take 25 volts to do the same thing AC, right? This is what you read on your meter when you're set to volts AC. That's the number you read right there, okay? This is the number you read on your oscilloscope for peak. All right. And then we have frequency, right? We know what our period is. It's 1 microsecond. So we have a period of 1 microsecond, which is 1 times 10 to the minus 6th. That's how long it takes to do one cycle. How many does it take? How many of those fit into 1 second? So if I take 1 second and divide it by that, that should be our frequency. Get used to using your scientific notation, right? On your calculator would be 1e 6 minus, and the reciprocal of that, 1 over that, would be 1,000,000. All right, so this would be equal to 1 million hertz or 1 megahertz. All right, mega. Get used to using mega for that. That's a capital M, capital H, little lowercase z. So the frequency of this is 1 megahertz. So that covers all the parameters of the sine wave in a sense, that everything we've studied so far. So I'm going to erase this and I'm going to put up a problem that I want you to turn in also at your lab so I can keep track of things. Okay, you did one in the first half. I'd like you to do this one in the second half. Okay, I have a problem on the board that you should be able to solve for the different parameters of the sine wave, and it'll be turned in at at your lab, your first lab, your second lab, depending on how this works out for timing. So again, I need these to see how well everyone is doing, and make sure you're not lost, and also some record of attendance of completing the lectures as well. So this problem, I am giving you a little twist up here, but you have to learn how to go back and forth. I'm giving you an RMS value of 120 volts. I'm giving you a frequency of 60 hertz. Okay, that is what very commonly we refer to as the line voltage and coming into your home. All right, that you're using right now someplace. With that, I'd like you to find the peak voltage, all right, the peak-to-peak voltage, and the period. So it's kind of a reversal of what we just did. You want to find the peak voltage, the peak-to-peak voltage, and the period from the frequency, and given the RMS voltage. That's problem number one. The second problem covers the average, and I'm giving you what I'm going to say. It's a fully rectified sine wave. It's the one that used the two diodes to steer the currents. So you always had positive peaks, all positive peaks. Given that we have 20 volts peak on these, what is the average or DC volts if I was to connect this like to a DC meter and read it? All right, what is the average voltage of that? 20 volts in, and the relationship is that number that we have for calculating average from peak. All right, give these a shot. Again, feel free to email me from the email that's on the first slide. Feel free to email me, and if you have a question and you're lost and I don't want anyone to fall behind. Everything we do in here is based on the last thing we did. So if you fall behind, we're in trouble. All right, so I want to feel free, please, to contact me at any point, and I'll answer your questions. Okay, good luck. We'll be coming up on our second lecture then. Thanks.